Hi, on the workbench today is a Miniware MDP-L1060 electronic load. This unit was provided to me by eDesign, the parent company of the Miniware brand. As usual, I will provide a link in the video description below for those who are interested in getting one after watching this video. On this channel, I have reviewed many instruments from Miniware, and the designs of their products are absolutely gorgeous, and this electronic load is no exception. First thing first, you will notice just how tiny this electronic load is. For the rated 100 watts maximum power dissipation, the size is actually quite impressive. One thing greatly enhanced the usability of this electronic load is that it has a built-in 650 mAh battery. And this allows you to operate this electronic load without having to plug it in. I don't know if there are any other electronic loads out there having similar feature, but this feature alone makes this electronic load stand out and makes it very easy to use. Although the load does have two rather powerful fans, so not entirely sure how long the battery will last if they are in full blast, given the 650 mAh battery. The packaging is also a little bit unusual. At first glance, there's nothing special about this box. If you open it up, let me just quickly open it up. By the way, I've already removed the electronic load, of course. You will see a smaller box with the included allocator testing clips. Nothing unusual here. Let me just pull this out. But the electronic load actually came in this beautiful acrylic box, as you can see here. The presentation is just gorgeous. And let me tell you, whenever I open a Miniware product box, there's always an element of surprise. They certainly put a lot of effort into the product design, and you can tell they're rather proud of it. Of course, you also get a product manual in multiple languages, and it's rather nicely printed out. Before I power it on, let's take a look at the specifications. As you can see, as far as the electronic load functionality goes, it is fairly standard. You've got constant current, constant voltage, constant power, and constant resistance mode to select from. The design is really clean and minimalist. We have a couple of standard banana jacks on the side for hooking up the load. You can even do remote voltage sensing using 4 wires with the XT30 connector here, and you do get a mating connector in the package, so you can make your own 4-wire sensing harness. Now, 4-wire sensing is useful if you are using electronic load to test batteries, especially when the load current is high. Without remote sensing, you will not be able to determine the cutoff voltage and could potentially damage your battery if it becomes over-discharged. On the front side of the electronic load, we have 3 buttons. They work in conjunction with a rotary encoder on the side for you to set the parameters of the load. And you can see we have 2 fans here, and the air blows directly across the copper heatsink and came out towards the back. We'll have to see under load what these fans sound like. And of course, you can use the USB-C port to charge and power the electronic load. I just zoomed in a little bit, just wanted to show you how beautiful this whole thing is designed and the attention to detail here. You can see the case is essentially made of aluminum and everything is very nicely put together. Looks like a very quality product here. And just want to give you an idea how small this electronic load is. Here I have a Miniware DS213 scope. In comparison, you can see that the width and length are actually similar to this Miniware DS213, which is already very tiny. Alright, now let's talk about the operations. To power on and power off the device, all you need to do is press and hold the set and menu key simultaneously, which we will take a look in just one moment. Like all Miniware products, you can also do firmware upgrades very easily when new firmware becomes available. And the way to do that is to press and hold the set and run key together, and it will boot into this DFU menu along with the serial number. Once you see this, you can plug it into your computer, and it will show up as a removable drive of roughly 500 kilobytes. If you have a later version of the firmware hex file, you can just drop it in, and it will automatically update the firmware. So that's very, very convenient. So now let's turn it off. And let's turn on the unit actually. So if you power on regularly, like what we did here, and then plug into a computer, it will show up as a 8 megabytes flash drive And you can actually write your test scripts and have the load run automatically according to the predefined steps. This is really cool, and we will take a look a little bit later. And before we proceed to testing, I just want to quickly show you the menu here. It's very intuitive to use. So here we can see we are currently in constant current mode, the CC here. And if I press set, we can change to constant voltage, constant resistance, and the highlighted parameter is where you can use a rotary encoder to change. So let's come back to constant current, for example. Currently we're setting at 0.3 amps, and we can change it to, say, 0.325 amps. And if you want to change faster, you can press and hold the set button and use a rotary encoder to change the readings accordingly. So it's very intuitive. And then we can actually get to the menu item here by press and hold menu. You can see here we have essentially the overprotection settings, and you can set. And the transmit and receive, that's for the optional display module. And this one is for the programmable feature that we mentioned earlier. And here you can adjust the sound volume. It's very intuitive here. Let's start with the constant current mode. This is probably the mode you would use it most. And the first thing we want to verify is the voltage readback accuracy here. So for that, I have turned down the electronic load to the minimum current. You can see 15 milliamps, and let's actually enable it. And as you can see at this voltage, we're actually showing quite a bit of discrepancy here. We're showing 0.021 on the load, whereas the actual measured voltage is about 0.028. So let's increase the voltage a little bit, and we'll see. Let's do roughly 1 volt, as that's an analog power supply. The output voltage is not controlled precisely, but anyway, right now we're showing 1.02, and you can see we're measuring 1.008. So the measurement is a little bit off on the electronic load, as currently we're not drawing much current. We're drawing just about 13 milliamps. So let's increase it to 10 volts. Roughly thereabout. And you can see we still have some discrepancy in terms of the measured voltage, and is in the 0.1 volt range. So let's increase it to 50 volts. And right now you can see that we are measuring 50 volts on the unit T, but we're only displaying 49.519 volts on the electronic load. So you can see we get about 1% of readback accuracy on this electronic load. And now let's take a look at the current measurement accuracy. And right now I have set it to the minimum current, which is 15 milliamps. And by the way, the fan is actually on. You can see it, but right now it's very quiet. And you can see already we have quite a bit of discrepancy on the reading here. We're measuring 24 milliamps, whereas the set current is 16 milliamp. So let's increase the set current to 20 milliamp, and we're measuring 30. So let's go to 50. And again, we have about 8 milliamps discrepancy here. So let's change it to 100. Again, we're 10 milliamps out. Let's change it to, say, 500. So now we're at 500 milliamps, you can see here. And we're drawing, again, consistently about 8 milliamps out. So let's change it to 1 amp. And by the way, the fan is started to spinning up. So let's change it to 1 amp. Not having a dedicated button actually makes precise current setting to be a little bit more difficult here. You just have to do the fine and coarse adjustment accordingly here. So now we're at 1 amp. Actually, the accuracy gets slightly better here, as we're only 5 milliamps out. So let's change it to, say, 2 amps. And it sounds like the fan is now speeding up. So it looks like we do have some current readback offset here, about 8 to 10 milliamps. And right now we're drawing 2 amps. Now what I'm going to do is I'm going to set it to 2 amps. As you can see here, I'm using the old one to verify the current reading, and I'm going to ramp up the voltage till we hit the maximum power draw here. So let's start ramping up the voltage. It sounds like the fan speed is linearly increasing. So right now we're about 30 volts and drawing about 60 watts. So now we're about, oh, okay, over power protection. Yep, because right now we're above the 100 watts mark. So let's actually ramp it down a little bit and let's reset it. So you can see we are able to draw the full 100 watts, no problem. But as soon as I increase above that watt rating, let's do that. And you will see that you will enter over power protection. Okay, let's do it again. Now, one thing which is a little bit annoying about the battery mode is if you leave it on and not touching anything, especially not in operation mode, it will power off within 1 minute, which is really annoying. So I think for the rest of the test, I'm going to plug it in. And since the maximum current is rated for 10 amps, I'm actually going to change the power supply and do the full current load test. So let me first change the current all the way up to 10 amps. And now it's at 10 amps. You can see. And now I'm going to start. So you can see we're drawing 95 watts. That's because we have some cable loss. But right now we're at the full 10 amps. And let's just quickly verify the current reading here. And you can see we're reading about 10 amps with no problem. I'm actually going to let it sit here for a while and take a look at the temperature of this electronic load. Alright, I have let it run for about 5 minutes now and it's under full load. So let's take a look at the temperature here. So don't know how well you can see it. Actually, let me adjust the camera here. You can see the maximum temperature is right about 61, 62, 63 degrees, and depends on how I measure it, is roughly there. That seems to be the maximum temperature as it has been running like this for a long while now. So the two fans are definitely very powerful and can become very loud when under full load. But it seems those are very high quality fans as at low speed you can barely hear them. Next, let's take a look at the constant voltage mode. This one is useful for testing charging circuitry. But for this test, I'm just going to use a current limiting linear power supply. In this mode, the electronic load will try to draw whatever current that is necessary to bring the connected source, whether it is a charger or it is a power supply, to the desired voltage. Of course, the current would be within the maximum current limit. So let's give it a go. And let's see, right now we're still in the constant current mode. So I press set. So now it's in constant voltage mode. You notice that the voltage here is at 3.3 volts currently. So let's actually change it to, say, 5 volts. And now let me enable the load. You can see that we're drawing 3.27 amps and the voltage is currently at 5 volts. So if I adjust the power supply current limit, you will see the current reading should change accordingly here. And it does. So that's the constant voltage mode. Next, let's take a look at the constant resistance mode. So let me come here and press it again. You will see now we're in the CR mode. So let's change the resistance to 10 ohms, as you can see here. Not sure if you can see it, but that's 10 ohms. And let me enable the load. So now we're at roughly 10 volts and we're drawing about 1 amp, so that's correct. So let me increase the voltage here. I don't know why oh, did you see that? It literally just jumped to 1.4 from 1 amp. So it seems like there's a lag. So let's do that again. Actually, this time let me put a clamp meter on it so we can see that, just to verify that we're seeing the correct reading here. So let's see here. It doesn't really matter if it's negative or positive, but right now we're drawing 1.44 amps. And let's bring down the voltage. And you can see we're not changing here. And it's probably going to take a few seconds. Yeah, so it took about 3 seconds for the current to catch up. So it does appear that there is a significant delay before the electronic load reaches a new current level based on the current voltage and set resistance value. For slow varying input voltage, such as battery for example, this slow adapting time should not be an issue. So this electronic load is probably not suitable for loading voltage sources with rapid change in constant resistance mode. And now let's take a look at the constant power mode. So for that, I'm going to change it to constant power, and we're drawing 10 watts. That's good. So let's give it a go. So at 6 volts, you can see 7 volts, we're drawing about 1.4 amps. That's 10 watts. That's good. And let me increase the voltage again. And not sure if you saw that again, we have similar issues. As I just increased the voltage, and you can see the current didn't change immediately. So let's do that again. So now I'm going to change the voltage down. And you can see, yeah, the change in current comes in at about 1 second after I change the voltage. So definitely there's a lag here. To be honest, I'm actually a little bit puzzled at the behavior in constant resistance and constant power mode, as it is understandable the control loop could potentially be slower because the calculation is done in a microcontroller, not in an analog feedback loop. But even with an MCU, you should be able to recalculate the current value relatively quickly, and it certainly would not take seconds. So I'm actually wondering if there's some other considerations or limitations. As I mentioned earlier in the video, besides these out-of-the-box functions, you can also program the electronic load, which is really powerful. On eDesign's website, you can download a sample script and you can tweak it to meet your needs. For some reason though, my Linux box thinks there's something wrong with the file system and refuses to mount it as a writable drive. This is interesting, as the DFU drive mounted as read-write just fine. Anyway, it's probably not going to be an issue for all of you Windows users. So the file I prepared essentially ramps up the current draw from 100 milliamps to 1 amp in 9 steps, and each step takes 1 second. So let's take a look at how it works. So let me go to menu, and let's cycle through, and let's actually select this one. So this is the file that I mentioned earlier, and run. So now you can see we're ramping up the current 100 milliamp at a time every second. And at the end, it takes a second to restart the program. So you can repeat your program up to 1,000 times, which you can specify within the program itself. You can also specify whether you want to run it in constant current mode, like what I did here, or in constant voltage mode. And let's take a look at the current here. You can see it's indeed 100 milliamps at a time. So in constant voltage mode, you can use this feature to mimic a battery's charging process. In my opinion, the programmability of this electronic load is perhaps the best feature, as it's very easy to use and is very useful as well. Well, it doesn't appear it's going to be easy to actually take the components out. It is not just the encoder cable here, as this can be desoldered easily. The problem is that it seems there are quite a few vertical boards in there, and I'm not entirely sure how they were originally put in. For example, you have this encoder board on the side, you can see. I'm not sure how this encoder is going to be coming out, because I try to pry it open, it doesn't really want to come out. And also you can see we have a screw here, not entirely sure if that is for securing the heatsink or not. It's just a little bit convoluted here. Also, there's some very thin magnetic wire coming from the bottom side. You can see here, not entirely sure what they're doing. But it does appear that everything was assembled fairly delicately. And it's not surprising they're using an STM32 variant here. The chip they used here is a GD32F303 VET6. And you can tell the heatsink is custom made. From this angle it appears that the heatsink is L-shaped, and the power MOSFETs would be pressed against the heatsink along this plane, and you can see the fans are blowing right across the heatsink fins. The designers certainly had put a lot of thoughts into the design. Alright, I think that's all I wanted to cover in this video. Overall, it is a nice compact little electronic load, although it does have a few issues here and there. If you liked the video, please remember to give it a big thumbs up, and remember to subscribe to the channel for more videos like this in the future. Your support makes videos like this possible. Thanks for watching, and I will catch up with you next time.